Martina. Preprocessing in QBF is extremely important. One of the first papers on this was co-authored by Martina on block clauses for QBF, and this is actually one of the most cited papers in QBF. And she also has been doing a lot of additional work on this topic later on, and also recently co-authored also a chapter in the new handbook, which also covers these techniques. I'm very excited to hear about what Martina will say about the preprocessing for QBF and how that impacts solving. Martina.
Thank you very much, Marijn. In principle, you already told the whole story. So preprocessing is very important for QBF solving. So nowadays, almost all solvers use preprocessors, are submitted with preprocessors to the competition. Otherwise, they would not work so well as they do nowadays. This relates not only to search-based QBF solvers, which are based on CDCL solving, but also to expansion-based solvers. And the only solvers which do not use preprocessing are those solvers which try to reconstruct the structure of a CNF formula and which then exploit non-CNF structure explicitly. But all other solvers nowadays use preprocessors. And here I have a good old cactus plot showing a picture we see with most recent preprocessors. So this is with my preprocessor blogger, and in the dark colors we have the solvers. We have 3 solvers here. Yeah, it's not a recent picture, but for recent solvers it's the same. In the dark colors we have the results for the solvers with preprocessors, and in the light colors without preprocessing. Yeah, it's a cactus plot. So on the x-axis we have the number of solved formulas, and on the y-axis we have the runtime. The more to the right we are, the better these results are. And we see that in all cases preprocessing considerably increases the number of solved formulas. And this is a picture we repeatedly see. And there is blogger preprocessor from Linz, there is a preprocessor from Freiburg, and there's also a lot of work on preprocessing by Florian Lonsing, which he did when he was at TU Wien. He's now at Stanford. And yeah, there are a lot of investigations also on preprocessings, and I would like to show you some of the most fundamental techniques which we found in most preprocessors nowadays. So before we jump into preprocessing, let's reconsider what a QBF is. We consider QBFs in Prinex conjunctive normal form. This means we have 2 parts in the formula. We have the prefix, the quantifier prefix, and we have the matrix, which is a propositional formula in CNF. We assume that the formulas we are considering are closed. This means that all variables have a quantifier, either an existential quantifier or a universal quantifier. And yeah, the propositional part is in conjunctive normal form. So we have a conjunction of clauses. A clause is a disjunction of literals as usual. And the important thing is that the ordering of the quantifiers imposes an order on the variables. So we do not have the same freedom as in SAT, where we can pick any variable to process next, but we have to be very careful about the ordering of the quantifiers. Otherwise, we would change the meaning of a formula. Important thing is that every formula can be transformed into an equivalent formula in a Prinex conjunctive normal form, or then satisfiability equivalent formula in Prinex conjunctive normal form. We also have a version of Zetin transformation, of Plesset-Greenbaum transformation, and in a similar way as in SAT, as Benjamin already explained, this transformations somehow blur information within the problem encoding, and this information is then harder to be used during solving, and the pre-processing techniques help to make this information explicit again and to eliminate redundancies. About the semantics, the standard semantics is when we have a QBF which starts with a universal quantifier, say for all x, then this formula is true if the formula which we obtain by replacing x by true is true, and if we set x to false is also true. And dually we define existential quantification, the semantics of existential quantification. At least one of the two formulas we obtain by replacing x by a true value has to be true in order that the QBF is true. And here I have an example. For all x exists y, and in this case I have x is equivalent to y, and in the case of the universal quantifier we have to check both values for the x, and in the case of the existential quantifier we need to consider at least one assignment to the variable to identify the true value of the formula. And in consequence, it's not enough, as in SAT, to consider one assignment of the variables, but we have an assignment tree as we have it here. So for universal quantifiers, we have 2 branches, and for existential quantifiers, we have 1 branches in a QBF model. And here I have again a summary of QBF models and countermodels. So here we have the model of a true formula and dually, and this is also a bit different as in SAT. In QBF, we have a duality between true and false formulas. So there is no easy part for the checking when we found a formula to be true, and just check if the assignment is indeed an assignment, but it's dual in QBF reasoning. And for a false formula, the counter models have the dual structure. Here we have 2 branches for the existential variables and 1 branch for the universal variables in the assignment tree. And it's important in a model, the assignments in the assignment tree or in the model make the formula true, and in a false formula, the assignments in a counter model make the formula false. And this is one representation of models and counter models for QBFs, but this is not very practical. What we are interested in practical QBF solving is to get so-called Skolem and Herbrau functions. In the case of a true QBF, a Skolem function is a function which describes the value of an existential variable based on the preceding, so on the variables to the left in the prefix, which are universally quantified. And the dual we have for false formulas, there we have so-called Herbrau functions, which give solutions to universally quantified variables. And we need these functions in practical QBF solving because they give the solution to the application problem. For example, if we solve a bounded model checking problem that is encoded in QBF, we want to have an error trace in case that there is a bug in the program that we are checking. Or if we are encoding a synthesis problem, we want to have the synthesized program. Or if we are using QBFs for game playing, we want to have a playing strategy. And therefore, we are interested also in getting these functions, and it's not enough for a QBF solver just to return true or false. This is short recap on QBF semantics. And now I come already to preprocessing techniques. So I have selected a couple of important preprocessing techniques, but there are many more. First of all, there are quantifier-agnostic preprocessing techniques which work as in SAT and do not take care or do not have to take care about quantifiers as we will see, there are many techniques which are similar as the techniques that Benjamin presented, but where we have to be careful about the quantifiers. But there are several where we do not have this issue. And the simplest one is tautology elimination. So if we have a tautological clause, as in SAT, we can simply skip it. Then we have subsumption, which is also defined as in SAT, and also self-subsuming resolution works for QBF. Benjamin already explained this, so I will not go into this in details again. Yeah, then let's come to the first important QBF preprocessing technique, which I would like to introduce, and this is universal reduction. And universal reduction is a very prominent technique in QBF research because it's the technique that makes the difference between QBF proof systems and SAT proof systems. So if you have a SAT proof system and like resolution, and then you get a QBF version of it by adding universal reduction, roughly speaking. And universal reduction was introduced in 1995 by Kleine, Bühning and others in order to give a resolution calculus for QBFs. And the resolution rule, the basic resolution rule for QBFs is similar as the existential rule that, or the SAT rule that Benjamin introduced. There are many variants of it, but in the first characterization, it principally worked like in SAT with existential pivots. And in order to make the proof system complete for QBFs, a second rule was needed, and this was universal reduction. And the idea behind universal reduction works as follows. So assume we have a QBF in Prinix conjunctive normal form and a clause. Then we take this clause and order the literals in this clause according to the order their variables occur in the quantifier prefix. And if we have a literal in the clause, in this sorted clause, that has no literal in this clause that occurs, whose variable occurs to the right of this universal literal in the quantifier prefix, and this literal is existentially quantified, then we can remove the universal literal. So let's look at an example. Here we have a QBF formula with a prefix exists X for all A, exists Y, exists C. And here we have this clause here, and this clause contains not X or A. And the literals are already sorted. We have first the outermost existential literal, and then we have the universal literal. And since there is no other existential literal which is to the right of A in the prefix, we can omit A. So I don't know if you see it, but A is now gray, so we can omit the A. And this is universal reduction. This is first preprocessing rule. And this is also used for transferring the concept of unit literals and unit clauses to QBF. In SAT, a unit clause is a clause of size 1. In QBF, we have a bit different definition of a unit clause. We say that a unit clause contains exactly one existential literal, and there may be an arbitrary number of universal literals, but they have to be to the right of the existential literal in the prefix. Yeah, so in principle, we could also remove them by universal reduction and then have only a clause of size 1, but the standard definition is to have this in this definition, including the literals the universal literals. And the existential literal is called the unit literal. And yeah, what's also important, if we have a clause consisting only of universal variables, then the formula is immediately false, because then we can remove the literals by universal reduction. What here is important is that we are very careful about tautologies. So the QBF rules always have side conditions about tautologies in order that nothing goes, to avoid that something goes wrong with tautologies. Yeah, but this is a topic on its own. So in our example, we have this clause here, which is a unit clause. X is not X is the unit literal. And if we have such a unit clause, then we can remove all clauses in which this unit literal appears and remove the occurrences of the literal with the opposite polarity. So here we can remove the X from this clause, and we can remove the other three clauses because they contain a not X. This is unit literal elimination in QBF, and this plays also a very important role in preprocessing. In QBF, what is also very important and what is also sometimes considered as part of PCB is pure literal elimination. So in QBF, we are happy with any technique that allows us to to avoid the quantifier ordering and have decisions early. And here an important rule is existential pure literal rule, and later on we will see there is also a dual version of it. And we call an existential literal pure in a QBF if only L occurs, but not L. So the literal occurs only in one polarity. And if we have such a pure literal, we can remove all clauses that contain this literal, and this existential pure literal can be at any position in the quantifier prefix. As soon as the literal has become pure, we can remove it. Here I have a formula, where I forgot to write down the quantifier prefix. This is, let's assume all variables are existentially quantified. Then so we have A or not C, C or not D, B or D. A and B are pure, so we can remove the two clauses. Now C or D is the only clause, C or not D is the only clause that is left. And we see that now, for example, C is also pure, and we can also, or not D is also pure, and then we can omit this clause as well and conclude that the formula is true. Yeah, and Benjamin talked about blocked literals and blocked clauses, and we have a similar thing in QBF as Marijn already mentioned. We introduced this quite a while ago. So this was joint work with Armin Bierer and Florian Lonsing. And this also plays an important, very important role in QBF preprocessing. And the definition of an existential blocked literal is very similar as in SAT, with the only restriction that we have to respect quantifier ordering in the context of QBF. So what we have to take care of is that, let's recapitulate what is a blocked clause. A blocked clause is a clause that contains a literal, L, and if I build all possible resolvents over this literal, then they are all tautologies. This is the definition in SAT. And in QBF, we have the restriction that the literals which form the tautology are to the left of the literal gives us the blocking property. With the blocked literal. And when we found a blocked clause, so a clause with a blocked literal, then we are allowed to remove the clause, and satisfiability is preserved. And as in SAT, it's a very powerful simplification technique because it can uncover some structure of the normal form transformation. It can simulate certain circuit optimization techniques. And yeah, it's a general generalization of existential pure literal elimination. Because in pure literal elimination, obviously we do not have any resolvents and therefore can immediately omit the clause. So the pure literal is a blocked literal as well. Here I have an example. We have the formula for all x exists y, and the not y here, for example, is a blocked literal, because if we build all resolvents, which is only one, we get x or not x, and this is a tautology, and therefore we can conclude that the first clause is a blocked clause. Obviously, the second clause is then also a blocked clause, and therefore we can conclude that this formula is true. In contrast, the x here, which is on the first position, is not a blocked literal. First of all, it's universal, and second, even if it was, now let's talk about this later. So it's not a blocked literal at the moment because it's not an existential literal. We will soon talk about a variant where we also consider universal variables. Yeah, and this can be even more generalized. And this was joint work with Marijn and Armin. And for QBF, we can also introduce a variant of the RAT rule, which is now very popular in SAT solving, and we called this QRAT. And yeah, I think I will go into the technical details, but here again, the important thing is that we have to take care about the dependencies, and RAT uses resolvents, and they have certain properties. And here again, it's important that we cannot use the full resolvent as we do it in SAT, but we take only a part which contains only literals with variables to the left of the literal which has the RAT, which is important for the RAT property. Yeah, and yeah, and if we have a clause which has this QRAT property with an existential literal, then this can either be used for clause addition or clause elimination. This is a generalization of existential blocked literals, and yeah, it can be even more. So QRAT uses propositional PCP for checking, and it can be even more generalized and use QBF PCP. And Florian Lonsing has a preprocessor which implements this, which uses QRAT and an extension of it for preprocessing, and this is also very powerful in this context. Yeah? Okay, yeah, but the main point I would like to make here, it's very similar as in SAT, the RAT property, only with the restriction that we have to take care of quantifier dependencies and may not take full resolvents, but only parts of it. Yeah, and then the question is, what is about universals? So if we consider this formula where we have swapped positions of the universal and the existential variable, so we have now exists y for all x, then if we perform resolution over the universal variable, we would get a tautology, and the question is, can we also use this? And when we simply would omit the clauses, then obviously a false formula would become true. And what we have here now is that we do not have, so all the techniques I presented before, so pure literal elimination, blocked clauses, and also QRAT transfer to universal literals, but there we do not eliminate clauses, but we eliminate literals. And so the definitions are, besides some technical details, very similar, but with these techniques on universal literals, we do not add or remove clauses, but we add or remove literals, and we require that they have the respective properties. So, for example, if a universal literal is pure in a formula, then we can remove it from all clauses. And similar with universal literal, with universal blocked literals or QRAT literals. Then very important in QBF preprocessing is universal expansion. This goes back to a solver Armin built in 2004, the Quanto solver, where he introduced the resolve and expand paradigm. And he observed that when we do expansion on universals, that the CNF structure is preserved, and expansion is extremely powerful in the context of QBF solving. And nowadays there are a lot of solvers that use expansion in combination with abstraction refinement approach. So they incrementally build build up an expansion of a formula until the formula can be decided. Here then SAT solver is used for deciding it. But in QBF, in preprocessing, in QBF preprocessing, we use expansion to eliminate certain variables, and this is a bounded approach of the Quanto approach. So if we have a QBF which has a universal variable A in the innermost universal quantifier block, so afterwards our existential variable, then the idea is to eliminate this universal variable by setting it once to true and once to false. And in order to get an equivalent formula, we have to be a bit careful about the variables to the right, about the existential variables to the right. In one copy of the formula, we have to rename them because they might depend on the variable which we eliminate. Yeah, and here we have some heuristics which say if it's a good idea to eliminate a universal variable. So we do not eliminate all, but only if the blow-up does not exceed a certain limit. And this is a very, very powerful technique in QBF preprocessing because it can shrink the number of quantifier alternations. Here I have an example. Here is exists X for all U, exists Y, and we eliminate the U variable, and we replace U once by false and once by top, and in one copy we rename existential variables and get a simpler formula. Then existential variable elimination. This is also very similar as Benjamin discussed it. This is also bounded variable elimination. We apply Davis-Butman on innermost existential variable. This also preserves CNF structure. Here, it's really similar as in SAT. If we do it on the innermost existential variables, there are also works which do it on other variables, on variables at other positions in the prefix, but then there are also some side constraints that have to be respected. And this also has to be done very carefully. in order to avoid exponential blow-up, but this can also help to eliminate certain sit-in variables and then give more structural information back to the solver. Yeah, here I have also an example, and we eliminate the y, and then there are two good things. On the one hand, if we build all resolvents, we get tautologies, and also the u is innermost quantified, and then we can apply universal reduction. Yeah, and if we now have a preprocessor and give a formula to it, then either we obtain a formula that is now different in structure and can then hopefully easier be solved by a solver, or often it happens that the preprocessor, mainly because of this resolve and expand paradigm that is partially implemented, solves the formula. And yeah, so then there's two challenges we worked on over the last years, and one is to validate the correctness of the results, and the other one is to extract solutions. So we want to have, especially for the true formulas, the functions. So if we get a solution for the preprocessed formula, then this is not a solution to the original problem, and for this some steps have to be taken in order to reconstruct the solution of the original formula. And for this purpose, we introduced the QRAT proof system. This is joint work with Marijn and Armin. And here we have rules for clause removal, clause addition, and clause modification. On the one hand, so clause removal and addition works with QRAT on existential literals. Clause modification we get with QRAT on universal literals on the one hand, and on the other hand, we need a generalization for universal reduction. And this we had to introduce in order to capture all all preprocessing techniques, in particular universal expansion. For this, we needed this universal reduction whole and this generalization of it. Yeah, so I don't have the time to go into details, but yeah, this is the rules we have in the proof system. And this leads us then to a tool chain, which allows us not only to check the correctness of the operations of the preprocessor by checking the QRAT trace. So we have checkers for the QRAT traces, and to check if the produced formula is correct. Simplified formula is really obtained by only doing valid transformation steps. And in particular, if the formula is solved, if the solution is correct. We also, this was also joint work with Marijn and Armin, have techniques to extract Skolem functions from QRAT traces in case the formula is solved. And with Katalin, Marijn and I also came up on a solution that gives us Skolem functions in case the formula is not solved by the preprocessor. Then we could show that we can extract a partial function or an incomplete function from the QRAT trace, which we can somehow compose with the formula obtained from the with the function obtained from the QBF solver. And this function, this composed function, gives us on the one hand the solution, and with a SAT solver you could again check the correctness of the result. By plugging it into the QBF, we get a propositional formula, check validity, and can decide that the result is okay. Yeah, with this, I come to the end of my talk. So in QBF solving, we have a lot of different solving paradigms, which are nowadays investigated and which give a very dynamic solving landscape. And very prominent approaches are based on Q-resolution and on expansion. They have very well understood proof systems. yeah, for Q resolution, it's also important. It's for both for expansion-based system and Q resolution. It's very important to notice that there are also variants of the proof systems with different strength. And somehow orthogonal to that, we have the QRAT proof system, which characterizes not only the preprocessing techniques, but in joint work with Florian and Marijn, we could show that also very powerful Q resolution-based proof system and expansion-based proof system can be captured by QRAT proof systems. Yeah, and with this, I would like to conclude my talk. I would also like to point out that there is a new book chapter in the Handbook of Satisfiability, which I wrote together with Olaf Beiersdorf, Mikolaš Janota, and Florian Lonsing. And in this chapter, we review the current QBF solving landscape, and there also preprocessing plays an important role. And there you also find details about the QRAT proof system, which I just quickly touched. Okay, thank you very much.
Thank you, Martina. Thanks for the very nice talk about this broad landscape of all these preprocessing techniques for QBF. I would like to, are there any questions for Martina? Maybe let me first start with a question. So what other kind of intrigued me, and I'm kind of wondering how you see this, is why is preprocessing so much more important for QBF than for SAT and MaxSAT? We've seen that they are important there too, but for QBF they are even more important. Why?
Yeah, I think in QBF the problem is that the normal form transformation is really bad, and this is a very difficult topic. So on the one hand, the simpler structure allows certain techniques and also allows us to have the powerful implementation techniques that come from the SAT world, like literal watching, or yeah, all the CNF techniques almost transfer to QBF. On the other hand, this CNF is not ideal for reasoning on universal quantification, and here the Zetin transformation does a lot of harm. It restricts also the freedom potentially. So the Zetin variables are not necessarily put at the end. They can also be put at different positions with some restrictions in the quantifier prefix, and this makes the reasoning more restricted. And yeah, I did my PhD on non-CNF QBF solving, and yeah, this and there were also many follow-up works investigating this, and it's good to have the structure in QBF solving, but it makes other things more difficult or impossible, and therefore I think preprocessing is a good compromise to deal with the structure loss and still have the power of CNF. Yeah.
Yeah, and it's also probably the reason why I think for the other representations, right, the non-PCNF formulas, preprocessing is less effective, if I recall correctly, right?
Yeah, and it has not been investigated to the same extent as for CNF, we also have to say. Yeah, so
Supratik also asked, do you know which of these preprocessing techniques have been actually lifted to first order logic?
Sorry?
So to first order.
Yeah, Benjamin mentioned this a bit. So yeah, this blocked clauses have been transferred there, and yeah, I'm not sure, subsumption, I guess.
I also think bounded variable elimination or predicate elimination, I think, has also been studied. And also there was a question from Ziad regarding whether the speakers are willing to share the slides.
Yeah, sure. So I'm happy to share my slides.
Okay, very good.
Sure.
I don't know exactly how to do this, but yeah, let's otherwise you can email me, and I can, anyone who wants the slides, then I can forward them. Yeah. Any other questions? Okay. Antonina says that they should appear on the Simon's webpage. So that's also, yeah. So please forward them to either to me or one of the other organizers, and then we take care of it.
Mm-hmm.
Yeah. And also, Antonina kind of mentioned that now we will start with the gather time, the tea time. So that is directly following this session. Any further questions? If not, then I would like to thank Martina and also thank all the other, both the other speakers for their excellent talks and to kind of this is great overview of pre-processing techniques in SAT, MaxSAT, and QBF. So thanks. It's a bit weird, I know, but yeah. I'm sure that there will be a lot of applause when we hopefully finally in not too distant future can have such a session again. Okay, thanks a lot, and hope to see you also. Okay, bye-bye.
Thanks, bye.